So we are now going to start the second chapter, relations and functions. Now in this chapter, we are first going to study relations, and then we will see a special type of relations known as functions. Now in order to study relations mathematically, we are going to introduce a fourth operation on sets. We have already come across three, right? Say A and B are sets. Then we have seen their union. This is one operation. Then their intersection. This is another operation. And there is also the difference operation. Besides this, we will now need something called the Cartesian product of A and B, and it will be denoted like this, A times B. Okay, using this fourth operation, we will express relations mathematically and we will study them. Now, in order to introduce this operation, we will have to know something known as an ordered pair. An ordered pair of objects or an ordered pair of elements. Ordered pairs are like sets, but there is a difference also. In order to see what these things are, let us start with an example. So this is actually the second 2.2. 2.1 is introduction. In introduction, we have these things. In 2.2, in the second section, we have Cartesian product of sets. And we are now going to motivate these things with an example. Consider the sets A. Say A is the set of the two colors red and blue. And B is the set of three objects, B, C and S, where B is a bag, C is a coat, and S is a shirt set. Now the question is, in how many ways can we color the objects, the elements in B using these two colors? In how many ways can the elements of B be colored using the colors in A? What are the ways of coloring these bag, coat and shirt? Obviously, each one of these items can be colored either red or blue, and accordingly we get these possibilities, these following possibilities. We can color the bag red. Okay, so let us enclose these two things within round brackets, within parentheses. We can also color the coat red, and we can also color the shirt red, or these items can also be colored blue, giving us these further pairs. So here we are looking at pairs, 6 numbers of pairs, 1, 2, 3, 4, 5, 6. And the pairs indicate the color and the object that is going to have that color, or maybe has that color already. Now these pairs are called ordered pairs. The fact that they are pairs is clear because each pair is a collection of two objects. For example, the first one has two things in it, red, a color, and an object bag. Okay. The second pair also has two objects. But what about this ordered? These are ordered pairs because the order in which we write these elements is it is now important, and that is why it is not exactly a set. It's an object. It is something that looks like a set, but actually it's not a set. For example, if you think of this ordered pair instead, B comma red. I mean, if we wanted, we could have written these ordered pairs. Well, I should not perhaps say like that, not these ordered pairs, but in place of these ordered pairs, we could have written 6 other ordered pairs, where the first elements are the objects in B, not the colors, and the second elements are colors. So you can see that in an ordered pair, there is a first element and there is a second element, and this one is supposed to be different from this one because the order has changed. This is not equal to this. Whereas if you think of the set consisting of these two objects, B and red, that is this set, then that is definitely equal to the set consisting of red and B, because in a set, the order in which you write the elements, it does not matter. And that is why, to emphasize that fact, we do not call these things simply pairs, but ordered pairs. In that sense, it is ordered. Once you fix the order, say you are going to write B first and then red, then this is one ordered pair and this is another ordered pair, although the objects in both of them are red and B. Okay. In spite of that, they are different because the order is different. So we can see that these are all the possible ordered pairs that show us in how many ways the elements of B can be colored with either red or blue. And the collection of all these ordered pairs, or the set of all these ordered pairs, is what we call Cartesian product of A and B. That is, if you take these ordered pairs and make a set out of them, this is a set whose elements, there are 6 elements in this set, each element is an ordered pair, then this set is considered to be the Cartesian product of A and B, which is written like that. But now we are going to see the actual definition, the formal definition of Cartesian product. And that definition is this, which is slightly different from this in the sense that it also tells us about what this A times B means if the sets A and B, maybe both or exactly one, is empty. Okay. So the definition takes into account that case also. So here is the definition. Note that the definition assumes that we know what ordered pairs are. Based on that only we have the definition of Cartesian product. Let P and Q be two sets if they are both non-empty, like A and B in this example, both are non-empty. Like that, if P and Q are both non-empty, then they are Cartesian. Cartesian is capital C, okay. It is named after Descartes, mathematician, so it's called Cartesian product. Denoted like this. And while reading it, you read P times Q, okay, is defined as this. P times Q is the set of all ordered pairs P comma Q such that P is an element in P and Q is an element in Q. If you look at this definition and try to see how that is the same thing as this thing, you can understand why this one and this one are actually the same. Here the only difference, because they look different, it's because this has been expressed in the set builder form, but this has been expressed in the roster form. If you want, you can express this A times B also in this form. If you do that, it will look like this. A times B is also equal to the set of all ordered pairs A comma B such that A belongs to A and B belongs to B. In other words, the first element is coming from A and the second element is coming from B. Keeping that intact, you have to consider all possible such ordered pairs, and this is the set of all such ordered pairs. And because the elements in A are the two colors, so small a can either be red or blue, and we can see that. In these three ordered pairs, the first element is red in all of them. And in these three, the last three, the first element is blue in all of them. Whereas the second element is coming from B, so it is either a bag or a coat or a shirt. So in that sense, we have defined the Cartesian product of P and Q. Also keep in mind that because we have to keep the order intact, the order in which the things are going to appear, so when you say the Cartesian product of two sets P and Q, do not change the order and write Q and P, that is something else, okay. Once you say the Cartesian product of P and Q, it means P times Q. Okay, so this is the definition of Cartesian product of P and Q when P and Q are both non-empty. But then what happens if, say, one of them is empty? In that case, what is the Cartesian product? If P is empty or Q is empty, then we define P times Q itself to also be empty. Now I want you to recall something. You remember that while defining the union of two sets A and B like this, we said a little something about this OR, that OR is inclusive OR. When we use OR like this anywhere in mathematics, in most of the places it means inclusive OR. This just means that either X is in A or X is in B or both. Okay, so that possibility is also included. That thing is true here as well. So P is empty or Q is empty doesn't mean that they cannot both be simultaneously empty. That condition can also be true. So this OR really means either P is empty or Q is empty or both P and Q are empty. In all such cases, the Cartesian product is defined to be the empty set. That means that this is what it means. Okay, so this is the full definition of the Cartesian product of two sets. Alright, so let us next see another example. Next, consider the sets, say A, consisting of these symbols DL, MP and KA, where DL denotes Delhi, MP denotes Madhya Pradesh, and KA denotes Karnataka. These Indian states. Delhi, of course, is not a state, it's a union territory. And, okay, we still have to write the other set. And B equal to 0, 1, 0, 2, 0, 3, consisting of codes of licenses of vehicles issued by these places, Delhi, Madhya Pradesh and Karnataka. In how many ways can a license be issued? And by that we do not mean the number of ways, but rather the ways themselves. So again, if you think of ordered pairs and say we agree that in a license plate of some vehicle, the place names, their codes like this are going to appear first, followed by these numbers, which are also codes. Keeping that in mind, we can think of ordered pairs where the first elements are coming from A and the second elements are coming from B. Then these are all the possibilities, of course. Let me keep DL constant first and consider all the numbers with that. Then comes MP. Oh, we have, okay, that's it, that's all for MP. And next comes Karnataka. Okay, so these are all the possibilities, and the set of these possibilities is clearly nothing but the Cartesian product A times B. If one wants, one can also consider B times A, but it's specifically mentioned in the text that we have to consider A times B. And that's why we said, or rather the text says, that let us agree that that on the number plates, these place names, place codes appear first, followed by these numbers. That's why we are considering A times B. Do you notice one thing? Because I have to erase these things, now itself I am saying this. In the previous example, where we had 2 colors and 3 items, the total number of ordered pairs was 6, which is 2 times 3, and it's understandable also why that happens. Because an ordered pair has 2 components, and the components are coming from 2 sets. So the total number of possibilities will be how many elements you have in one set times the number of elements in the other set. So in that example, we had 6 ordered pairs. Here, however, because we have 3 elements in both A and B, so in total there are 9 elements in A times B. Are there really 9 elements? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. And let us take another example which is somewhat abstract. Abstract means here A and B are just some sets. Next, consider the sets. So this third example is not going to talk about anything from the real world. So here A is just the set consisting of 2 objects, A1 and A2, and B is the set consisting of these 4 objects, B1, B2, B3 and B4. These are supposed to be distinct objects. I mean, within the sets they are distinct, right? In other words, A has 2 elements, that means A1 and A2 are different objects, and B has 4 elements. So these are also distinct objects. We may, however, have something common between A and B. when you form the Cartesian product of two sets, it's not necessary that the sets have to be disjoint. You may have the same element also in both A and B. We will come across such examples, but let's see here in this case what the Cartesian product is. Then A times B. Okay, now when you try to find out all the possible ordered pairs, what do? This is perhaps the best way. First you fix an element of A, and with that element as the first element of your ordered pair, you then vary the second element over B. In other words, I am going to first of all consider those ordered pairs where the first component is A1. The second component can then be B1 or B2 or B3 or B4, and then I change the first component. Now my first component is A2. With A2 as my first component, the second component again can either be B1 or B2 or B3 or B4. Okay, so this is A times B. And now there is something else to talk about it as well. You may notice that this looks somewhat complicated. It is actually. At least when we see these things for the first time. There are many commas, there are many round brackets, there are also curly brackets. So you may get overwhelmed by these things. At once, if you look at this really looks messy. And you may lose track of what you are writing, and you may in fact forget to write some commas, or you may even forget some brackets. If you do, then that's a mistake. How to avoid such mistakes? You see, keep in mind that this is itself a set after all, right? And its elements are ordered pairs. Just like we separate the elements of a set using commas, we have these commas. Commas between consecutive ordered pairs. But an ordered pair as an object of its own type itself also has a comma inside of it. So if you are somewhat confused about what to do, you can first do this. Of course, you have already seen how I have written this entire thing, but because I have written it many times, so I have got used to all the complexities. So what you first do, you do not write the commas in the ordered pairs. You simply write A1, B1, enclose them within round brackets, followed by comma A2, B2, as if you are writing a set, and you are in fact writing a set. So first you write these elements, and once you have finished writing this, then you insert the inner commas. This will help you avoid making mistakes. Okay. And once you finish writing everything, do not forget to enclose all the things within curly brackets. Whenever we talk about sets, always use curly brackets, unless we are talking about intervals. In that case, we use square brackets, round brackets. That's a different thing. All right. Now, finally, there is, of course, the question of how many elements this one has. The previous two examples were, in the first one we had 6 elements, 6 ordered pairs. Then in the second one we had 9 ordered pairs. Here we are going to have 8. 1, 2, 3, 4, 5, 6, 7, 8. Why? Because A had 2 elements and B had 4 elements, and 2 times 4 is 8. Now there are some remarks about all these things. So let's see the remarks one by one. There are 4 things that the text remarks about. The first one is, of course, all these remarks are very important, okay? So pay attention. 2 ordered pairs are equal if and only if their first components are equal and their second components are also equal. In this form, the statement looks somewhat complicated. So let us express this mathematically. In other words, for 2 ordered pairs, A comma B and C comma D, we have A comma B equal to C comma D if and only if A is equal to C and B is equal to D. That's what this means. And one more thing before we before we see how this is the same thing as this, what do you say? Verbally, what do you say when you look at this? How do you read this? To read this, you just say A comma B, ordered pair A comma B. When you hear this, you have to write this. Or if this is written, you have to read it like this, A comma B. So let's see what this one says. 2 ordered pairs are equal if and only if their first components are equal. The first component of this one is A and the first component of this one is C. If they are equal and the second components are also equal, which are B and D respectively, they are also equal. This condition for equality of 2 ordered pairs keeps in mind that the order stays intact. Now you can now see why we have, for example, this. Say we consider the ordered pair whose first component is 1 or the ordinary number 1, the integer 1, and the second component is 2. This is not equal to 2 comma 1. That's because 1 is not equal to 2 and 2 is not equal to 1. Although the sets 1 comma 2 and 2 comma 1 are equal. The definition of this equality and the definition of this equality are entirely different. Here we just have to keep in mind that every element of this set is also there, and conversely every element of this set is also there, so that each one is a subset of the other. That is ordinary set equality. But an ordered pair equality is somewhat different. There you see these words appear: first, second, okay, which are absent here. In a set there is no first element, there is no second element. Okay, so you have to keep this condition in mind. So that is the first remark. And then the second remark, of course, tells us about what we have seen in the three examples, that the number of elements in the Cartesian product of two finite sets is the product of their numbers of elements. If A and B are finite sets with A having P elements and B having Q elements, then A times B is also a finite set having PQ elements. That's how we got those numbers. In the first one we had 6 elements, in the second one 9, and in the third one 8. Now suddenly you may have realized something about the Cartesian product. All the examples we have seen so far involved only finite sets. Both the sets whose Cartesian products we considered were finite. That, however, is not necessary, because the general definition does not assume finiteness. In the general definition, that those sets P and Q may be infinite also. And this third remark is about that. If A and B are non-empty sets and at least one is infinite, then the Cartesian product is also infinite. Now let us not just leave this remark here itself like this. Let's see one or two examples of this kind, because all the things we have seen so far were about finite sets. What infinite set can we take? Let us take the set of natural numbers itself. Consider the Cartesian product, but at the same time we have to keep it simple. Okay, so let me take like this. Where now our first set A is this singleton set, and the second set is the set of natural numbers. Of course, by the definition of Cartesian product, this will be what will be the set? This will be the set of all ordered pairs A comma B, such that A belongs to 1 and B belongs to n. In other words, it is the set of all ordered pairs where the first component has to be equal to 1. That is the only possibility here. And the second component can be any natural number. So now I can write this set I can express this now in roster form, like how we express infinite sets using ellipses, the 3 dots. This set is, see, the first component is fixed, it's 1. It cannot be anything else. But the second component can be any natural number. Dot, dot, dot. So you can see that both the sets are non-empty and one of them is infinite. And the Cartesian product is also infinite. It's not finite. If you start counting, you will never be able to finish in a finite time. Next, consider, for example, this Cartesian product. Okay. Here, however, the first set is empty and the second set is infinite, but the second set being infinite has no effect on the result, because by definition, if at least one of the sets is empty, then the Cartesian product itself is empty. So in spite of this being infinite, we end up having empty set because this is empty. This is somewhat like multiplying a very large number by 0. No matter how large that number is, the result is 0. Okay, it is somewhat like that. But of course, I am not going to write something like this. Okay, do not use or even think about it, at least not right now. And don't write this equal to infinity or 0. These are some delicate things, okay. Let's forget about them right now. Let's ignore them. This was only simply an analogy. Finally, let us also consider this. Here both the sets are infinite. Fine. That is also possible. Again, by definition, it is the set of all ordered pairs A, B such that A belongs to N and B also belongs to N. In other words, now both the first and the second components are coming from N. If you, however, want to write this in roster form, you will encounter a little problem, because you won't be really able to, in what order will you write? If you choose the first component to be 1, there itself you cannot complete writing this, but then the first component can be 2 as well. So this set is rather inconvenient to write in roster form, but it's a set nonetheless. It's a very big set, and looking at the elements, you immediately notice one thing, that this is a subset of this, a proper subset in fact. Both are infinite, but the elements of this set seem to be only this much, whereas the elements of this go far beyond that. Okay, so that was the third remark. And there is a fourth remark also. Suddenly why they decided to bring this here, I don't understand, but anyway, it's there, so we have to see it. My only objection is that they should have talked about this thing in the, not in a remark but in the main text itself. Main text means maybe after defining Cartesian product itself. For any set A, there is also something like this. The Cartesian product of, this is also a Cartesian product, although this is not covered by our original definition because there are only two sets are involved. Here, however, we have three sets, and for some reason these three sets have been taken to be the same. The elements in this are not ordered pairs, but they are ordered triples. These objects are also like ordered pairs, but three objects are involved. Instead of having two objects, here we have three objects. But that aspect that the order should be maintained is present here also. That's why these are called ordered triples or ordered triplets, where A, B and C are all coming from A. There is no need to have these three the same set. You can have another set B here and another set C here, and accordingly the definition will also have to be written. But anyway, we just suddenly out of nowhere, without rhyme or reason, the authors have decided to talk about this. So what can you do? So these are the remarks. Now, to illustrate all these things, there are some examples. Let's now next see those examples. These next examples explore some further things about Cartesian products. The first example, it is something about ordered pairs themselves. Example 1, I think. If the ordered pair x plus 1 comma y minus 2 is equal to 3 comma 1, find the values of x and y. And here you have to use the condition for the equality of two ordered pairs, namely their first components have to be equal and their second components have to be equal. Oh, by the way, when you see an ordered pair like this now, that 3 is also sometimes called the first coordinate and 1 the second coordinate, although this term coordinate is really something that comes from geometry. That's why in general we say first component and second component, but if you want, if that sounds nicer to you, then you can also say 3 is the first coordinate and 1 is the second coordinate. But anyway, let's not now find x and y. Since x plus 1 comma y minus 2 is 3 comma 1, we have, what shall we have? The first components have to be equal. That is, x plus 1 has to be 3 and the second components also have to be equal. Hence, x must be 2 and y must be 3. So this example tests if you have really understood when two ordered pairs are equivalent when they are not. Next example 2. If here two sets are given, the first one is the set consisting of three objects A, B and C. And the second one has only one object. Then form the sets P times Q and Q times P. There is no reason you have to find only one Cartesian product. You can also find the other one, changing the order. Are these equal? Okay, so without writing sentences much, let's just straight away find the sets. So P times Q will consist of all ordered pairs where the first component is going to come from P and the second one is going to come from Q. So the second one can only be R, but the first one can be A, B or C. So we will get these ordered pairs: AR, BR and CR. That's it. And you may also verify that remark about the number of elements in P times Q. P has 3 elements, Q has only 1 element, and 3 times 1 is 3. So P times Q should have 3 elements. Yes. And what about Q times P? This time, however, the first component has to come from Q. So that means the first component is constantly R. RA, RB and RC. So obviously these are not the same set. Because the elements, although they are ordered pairs, and in spite of the fact that the same number of elements are there, this one also has 3 elements and this one also has 3 elements, but they are still not the same set. For example, this ordered pair R, A is absent in this set. No ordered pair here in P times Q has its first coordinate R. So it's kind of a product of two sets, right? So unlike ordinary product of numbers, set product is not commutative. 1 times 2 is equal to 2 times 1, always. Okay, if you multiply any two real numbers, A and B, AB is the same as BA. That's not the case here. Next, let A have the 3 elements 1, 2 and 3, B have the 2 elements 3 and 4, and let C have 4, 5 and 6. Now we have been asked to find some products. Find the following. Number 1, A times B intersection C. Now what will happen if we bring in the other operations as well along with Cartesian product, say we consider intersection? We can do that. Number 2, A times B intersection A times C. Number 3, A times B union C. And number 4, A times B union A times C. Now note that unlike some such things which involve only say union, intersection and set difference, for these we do not have any laws, like for example we do not have De Morgan's law or anything like that that may help us simplify things. No, you have to do exactly what is given. Okay, there are laws but we haven't seen them. So we are supposed to just simply calculate directly. Yeah, in the presence of any loss, if we are still following a very lengthy operation without using any such loss, then that is simply dumbness, that is foolishness. But now we do not know anything. So the first one is A times B intersection C. And maybe you remember I was saying just now, it's not necessary for the sets involved to be disjoint. Here for example, you have a common element 3. B and C have a common element 4. So like that you may have common elements. A times B intersection C is for the only common element? Yes. Oh, so that itself makes the job slightly easier because here you have only 4. Alright, so now what will you do? You see, this is going to be the set of ordered pairs where the first component is going to come from A and the second one is fixed, it's only 4, there is no other option. The first component however can be either 1 or 2 or 3. Accordingly you will get these ordered pairs. Have you noticed one more thing? I haven't actually written what the set A is. This is not advisable in the exam. In the exam you do write everything, okay? In place of A, do not just simply jump from this to this. There should be a step in between where you write what A is and then you write this. The number 2, A times B intersection A times C. The intersection may be small, but we do have to find these two sets first. So what is A times B? This will be somewhat big, so be careful. Again, keep that in mind. First you fix one element of A and change the second coordinate over B. So that way we are going to get 1, 3, 1, 4. And then you change the first component. Let that be 2 now. 2, 3, 2, 4. And finally 3, 3, 3, 4. You see, because we have a common element between A and B, so you can have 3, 3. That doesn't cause any problem though. Intersection, then A times C. Same thing, but this is going to be bigger. Let the first component be 1 first. 1, and the second component can be 4 or 5 or 6. So 1 4, 1 5, 1 6. Then the first component can be 2, 2 4, 2 5 and 2 6. Let me keep the sets, okay, and continue from here. 2 4, 2 5, 2 6, and then finally 3 4, 3 5, 3 6. Okay, and what do ideally I should not write like this, no? I should write in the next line. And again, don't forget to close bracket. Now I have to find the common elements. Do we have 1 3 here? No, we won't have 1 3 here, because in C there is no 3. Okay, so this is ruled out. Of course, in your actual calculation you do not use such symbols. If you find it difficult to figure out, ultimately what you will have here, do a rough work alongside your actual solution. 1 4 we have, okay. What about 2 3? Again, 3 cannot be the second coordinate here. So these elements having the second coordinate as 3 are already ruled out, and we have 1 4 here. What about 2 4? Yes, we have 2 4 here. What about 3 4? Yes. And just like here in this second set of intersection, we cannot have 3 as the second coordinate of any ordered pair. Here we cannot have 5 or 6 as the second coordinate of any ordered pair, although here you have 5 and 6. That's because 5 and 6 are not there in B. So these ones, these ticked ones, are the common elements. 1 4, 2 4 and 3 4 also we have now. Oh, so I didn't put a tick here. 1 4, 2 4 and 3 4. So you see that although the original sets this and this are big, but the intersection is not really that big. Then next, A times B union C. And the final one is, okay, this is going to be really big. A times B union C. B union C is 3 4 5 6. All right. So 3 times 4, there will be 12 elements. 1 3, 1 4, 1 5, 1 6. Two 3, 2 4, 2 5, 2 6, and finally 3 3, 3 4, 3 5, 3 6. And finally the last one, the fourth one, A times B union A times C. Oh, we have to write it again. No, in that one we already had these two sets. But anyway, we have to. So A times B, 1 3, 1 4, 2 3, 2 4, 3 3, 3 4. Union A times C. 1 4, 1 5, 1 6, 2 4, 2 5, 2 6, then 3 4, 3 5, 3 6, and now it's not intersection, it's union. So be patient, we will just write all the elements of A times B and A times C, keeping in mind that we should not repeat any common element. So let us first simply write all the elements of A times C, because anyway we have to write them. One 5 1 6, 2 4, 2 5, 2 6, 3 4, 3 5, 3 6. All right, and then we see if we have anything extra here. Yes, we have 1 3. You just see all the elements one by one. 1 4, do you have one? Okay, we already have 1 4 here. Fine, there is no need to write once more. 2 3, 2 3 is not present here. Next, 2 4, yes, you have 2 4 here. 3 3, it was not there, so it has to be written. Then 3 4, I believe 3, yes, 3 4 is here. That's it. How big is it really? It's not really that, it's not anything impossible. Then the next one, I lost count because I haven't written any numbers here. So let me just simply write example. If T is the set 1 comma 2, form the set P times P times P. Oh, it's for this, that fourth remark is there. Alright, now we have to be a little careful. Now we are not going to write ordered pairs but ordered triples, where all the components, now there will be a third component also, all the components are going to be elements of P. So let me first fix the first component as 1. Now the second component and third component can also be 1, or the second component can be 1, the third can be 2, or we may have 2 1 or 2 2. Next, so these are all the possibilities in which you can have second and third component, keeping the first component 1. Next, you repeat all these things but with 2 in place of the first one, so that now you are going to get 2 1 1, 2 1 2, like that. Two one two, 2 2 1, and finally 2 2 2. Here also a similar remark can be made about the number of elements. You see, P has 2 elements, so P times P times P should have 2 times 2 times 2, that is 8 elements. Yes, that is true. 1, 2, 3, 4, 5, 6, 7, 8. Next example. What do the Cartesian products this R times R and R times R times R represent. Okay, I am writing this R, which looks quite complicated, but this is standard symbol which denotes the set of real numbers. You just simply write R. Okay. We have x comma y such that x and y belong to R. So looking at this, you can clearly see that this set represents the set of coordinates of all points in a two-dimensional plane. Once you have chosen an x-axis and a y-axis, that is a Cartesian coordinate system in the plane. Once you have chosen that, then each point can be associated with a coordinate. A coordinate means a pair of coordinates. In fact, this is the place from where the idea of Cartesian product originates. And that is why we say Cartesian coordinate system. So, this represents means is the set of coordinate, let me write like this, coordinate pairs of points in a plane. There's no need to write a two-dimensional plane. At this level, saying plane means a two-dimensional plane, a flat surface. Similarly, this is the set of all ordered triples of real numbers, and this represents or is the set of all coordinate triples of points in space. Just like you can have a Cartesian coordinate consisting of an x-axis and a y-axis in the plane, you can have such a coordinate system in space by introducing a z-axis which passes through the origin of that xy system. You can then, just like the plane Cartesian coordinate system, assign to each point in space a an ordered triple of real numbers. That points x coordinate, y coordinate and z coordinate. Okay, so this is the set of such coordinates. In fact, in higher geometry, this itself is called the plane and this itself is called the three-dimensional space. And finally, there is another example. This last example is going to ask something in the reverse direction. Here we are no longer given two sets whose Cartesian product has to be found, but rather Cartesian product itself is given. We have been asked to find the sets. If A times B consists of these ordered pairs P comma Q, P comma R, M comma Q and M comma R, find A and B. So this you have to do by inspection. The solution doesn't offer any real explanation or anything, you just see from inspection. We find this. What should A be? What should A have? A should have those elements that have become first coordinates of these ordered pairs. And the first coordinates are P and M. So, A should consist of P and M. And similarly, B should consist of the second coordinates of the ordered pairs, which are Q and R. To verify that you are right, you try to think of A times B now that you know A and B. A times B should have the pairs P comma Q, P comma R and M comma Q and M comma R. Yes. Okay, so these are A and B. And with that, this section is over. After that, there are of course exercise problems which we will solve on Thursday in the community section. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.